If you've got the Oxford or Cambridge interview and you apply to do maths or anything STEM based, likelihood is you're going to have to sketch a graph at some point in your interview. My name's Jamie and I studied maths at the University of Oxford, and now I help students all across the globe who are looking to study maths at these top universities get in. I'm going to be showing you how I would, in an interview, sketch this graph. So we've got y squared equals x sine x. So this is slightly different to ones maybe you've seen in school because it's not in the form y equals a function of x. So that's just something to bear in mind. It's y squared equals x sine x. But, and as I reveal in a second, that actually can help us a little bit in terms of sketching this. So, as I say, with most of these kind of problems, I encourage you to pause the video and actually have a go at attempting this problem as if you were in an interview. Maybe even record yourself doing it, then come back, watch me explain it, and then maybe 20 minutes later, go and record yourself doing it again, now with the advice I've given, and then look at the difference between the two. Look at how much you've improved. Look at the skills that you've learned. That's kind of why I make these videos, to help you improve and prepare for these interviews. Anyway, that's enough of me rambling on. Let's have a look at this problem. We've got y squared equals x sine x. I mean, imagine the interviewer has just asked me to sketch this, and now I'm going to go into interview mode, and I'm just going to stay in interview mode throughout. Then at the end of the video, I'm going to hopefully have a perfect graph of this, but then also explain the things that I did well in my explanation, which is what would have got me an offer to study at Oxford, which it did a few years ago. Anyway, let's dive right in. Okay, so thanks for this. This is an interesting looking curve. I firstly noticed it's not in the standard form of y equals f of x, but nonetheless, a bit more challenging, but I'm up for a challenge. So whenever I like to sketch a graph, there are several things I like to consider first. Firstly, perhaps the domain, and maybe the range as well, but also things such as if there's any symmetry in the curve, and if the curve is periodic, and also then some of the kind of more standard things, so intercepts, any asymptotes or limiting behavior, and perhaps what happens at stationary values as well, or if the curve has any stationary values. So I'm going to start by thinking about the domain. From the looks of it, in terms of x, there's no real restriction. I guess I do have to be careful because y squared has to be at least 0. I'm assuming we're only going to work with real numbers here. So since y squared is at least 0, x sine x, either x and sine x both have to be positive, or they both have to be negative, or I guess one of them could be 0 as well. That's one observation, which I'll maybe come back to later. In terms of periodicity, it doesn't look like this curve is periodic, although it does have a sine x in. Annoyingly, oopsie, this x in the front of it kind of means that it's no longer a periodic function, but I do imagine that it may have some kind of oscillating kind of behavior, but again, that's neither here nor there. In terms of symmetry, this is a bit more promising. So I do notice that this graph has symmetry because if I swap the y for a minus y, so if I had minus y squared and kept the x's as they are, then I get the same curve, x sine x. And so that tells me that this curve has symmetry in the line y equals 0, namely the x-axis. So this graph has symmetry in the x-axis. Furthermore, I also notice it has symmetry in the y-axis very nicely because x sine x is an even function. If I replace the x's with minus x, I get minus x times sine of minus x, but since sine is an odd function, I can bring this minus out to the front, and that will just give me x sine x. And so that tells me that this graph also has symmetry in the y-axis. So this is pretty cool. This curve has symmetry in both the x-axis and the y-axis, which makes my job a bit easier because when I'm sketching it, although it's going to be defined in all 4 of the quadrants, I'm actually just going to focus on the top right quadrant and what it looks like there. And then I can reflect it over into this bottom quadrant because it's symmetric in the x-axis, and then work out what it looks like in these 2 quadrants by reflecting it over in using the fact that it's symmetric in the y-axis. So that makes my job a lot easier. I can just focus on this top right quadrant to begin with. So let me draw up some axes here. Okay, so we're looking in this quadrant where x and y are both positive, which is nice, which means that when I square root both sides, I can just take the positive root. I still, of course, need to be careful about sine x here. So although x is positive, I need to ensure that sine of x is positive as well, or non-negative here. And that actually tells me some stuff about my domain, because at least in this interval, or in this quadrant, I know that sine of x is only at least 0 when x is like between 0 and pi, and then 2 pi and 3 pi, 4 pi and 5 pi, and so on. So if I mark this on, 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, well, I'll do a couple more, 6 pi, and 7 pi, like so. And I know that between 0 and pi, sine of x is positive, or at least 0, but between pi and 2 pi, sine of x is negative, so this graph won't be defined. Okay, so that's just something to bear in mind. So there won't be anything in this like interval of our graph. Fine, not a big deal. So now I guess the next thing is to think about what this actually looks like in this quadrant. Well, in terms of intercepts, well, we know it's going to have roots at these points, at the multiples of pi, because sine of n pi is 0, and those are the only intercepts in this quadrant. And the y-intercept, well, when x is 0, y is 0, so it's going to start off here at the origin. Okay, the next thing I'm going to consider is if this graph has any asymptotes, and by the looks of it, it doesn't look at least that it will have any vertical asymptotes, because vertical asymptotes generally occur when either you're dividing by 0 or perhaps you're taking the logarithm of 0, but that isn't the case here. And as x, and now I can maybe look for horizontal or potential oblique asymptotes, and yeah, I can see that as x approaches infinity, we're going to get something interesting happening, because we've got the square root of x, which will approach infinity. But sine of x is going to kind of oscillate up and down between -1 and 1. And again, we know it has infinitely many roots at these multiples of pi. So in fact, if I sketch y equals root x like this, so this is y equals root x. And because I know that the biggest sine x can be is 1, I know that y is always less than or equal to root x in this quadrant. And so actually what I can do is use this as a model to help me sketch this. So I know, let me sketch y equals x, root x sine x in blue. I know that it's never going to go above this red curve, and in fact it's going to equal this red curve when x is pi over 2, 3 pi, not 3 pi over 2, sorry, 5 pi over 2, that would be 9 pi over 2, that would be 13 pi over 2, because at those values, 13 pi over 2, 9 pi over 2, and so on, sine of x is 1. And so y would just equal root x. And so in fact, I can just kind of use this to kind of sketch this out. It's going to look something like that between 0 and pi. And then, as I said earlier, there'll be nothing between pi and 2 pi. Between 2 pi and 3 pi, it's going to look something, like this. Between 4 pi and 5 pi, again, something, just like that, and so on, and 6, and like so. So I should be clear, the turning points aren't necessarily at 9, well, in fact, it's not going to be at 9 pi over 2, because we know that the gradient of the square root of x graph is positive, but we know that when x equals 9 pi over 2 or 13 pi over 2, these blue numbers on the x-axis, the y values are going to be in line, the y values are going to be on the curve y equals root x. Okay, and so this is what this curve will look like in the top right quadrant. And now, as I said earlier, because of the symmetry we observed, we can just work out what this will look like for all values of x by reflecting it in the x-axis and then in the y-axis. So roughly speaking, it will look something like this. Well, if I draw it just for the positive values of x first by reflecting it here, maybe something like that. This is not very symmetric, but hopefully you'll excuse me there. And then for negative values of x, again, we're just going to reflect this in the y-axis because of the symmetry we observed earlier. Oh, this is horrible. But hopefully you get the picture. And that's what this would look like. Boom. That's it. Done. Mic drop. That is how you can sketch a curve like this. So that would be a very, very good answer to this question. And they may have follow-up questions, something to do with this curve. They could ask you to work out some areas or whatever, whatever. They could do some follow-up stuff, but this type of question would at least take 5 to 10 minutes for a good student. I'm not sure how long this has been going for, but you can see that I explained it in a lot of depth, and hopefully I made it very clear to you why I was considering the things I was considering when I was, and how I kind of got from a blank screen to this final image of this graph. What are some of the key things that I did? Well, firstly, at the start, I laid out my ideas. I told the interviewer exactly what I was going to consider. So I told them, okay, cool, I know what I'm going to consider. I want to consider the turning points, the incepts, blah, blah, blah. And I just told them that. That way, the interviewers have an idea of the next steps. And it feels, from their point of view, a little bit more under control. They know, okay, cool, this student has said they're going to work out the turning points, they just haven't got to it yet, fine. Whereas if, let's say, for whatever reason, for this problem, we really needed to work out the turning points, and you were just being a bit slow in terms of sketching the graph, the interviewer might be like, oh, maybe this student hasn't thought about finding the turning points. But if you say it right at the very start that you're going to consider all those things, they know, cool, the student will get around to it. It's just that they're calculating something else at the moment. And so that's really, really important. Secondly is observing symmetry. That's going to save you a lot of time. You saw here, that was one of the first things that I did, and we saw how much time that saved me. It meant that I could literally only focus on 1/4 of the whole image. And it's also quite nice because it's the top right quadrant where X and Y are positive. With these sorts of things, it can get quite fiddly when you have to think about negatives and stuff. I personally love to deal with, much prefer to deal with positive numbers over negative numbers. So that's kind of why it's useful to make that kind of investment of time at the start to observe that symmetry, to then mean that, cool, I just need to focus on one quadrant and then I can reflect it over to get the rest of the diagram. And making that clear. So also why I was looking for symmetry was that if this graph was periodic, obviously it's not, but if they'd got me to sketch a graph that was periodic, I could say, okay, I'm only going to look at the sketch within a certain interval and tell that to the interviewer. And then I could say, well, the reason for this is once I've got it in this interval, since it's periodic, I can just copy and paste it over and over as many times as I need. Those were some of the big things here. And also I think this fact that I drew the y equals root x graph kind of helped, because it kind of made it a lot clearer why we get these increasingly taller humps, I guess, for this curve. But yeah, as I say, do give this problem another go. So hopefully you listened to what I said and you had to go before you watch my solution. Have a go yourself. Maybe not right now. Maybe later on this today, or whenever you're watching this in a few hours time, just so you have a time to actually digest some of the techniques and stuff, and record it. Recording it is so useful because it means you can watch back your performance. It's so difficult to tell how you're doing in the heat of the moment because you're focusing on a million other things. Record it, watch it back, and if you want to, keep a log of your videos, and then that way you can see your progression over time as well. And yeah, if you can, try and do like a post-match analysis where you look back in your report, on your recording, and go, okay, cool, this is what I did well, this is what I could improve on. Anyway, I'll leave a video on screen where I show you how to sketch a different type of graph, because as I say, graph sketching is almost something that will definitely come up. So it's just useful to do lots and lots of reps. Just sketch lots and lots of graphs, practice explaining all the things you need to be able to sketch a graph. But yeah, if you're doing any kind of STEM interview, it will almost certainly be guaranteed to come up in at least one of your interviews. So best of luck. And hopefully, as of at least recording this, a few of my students have started to receive interview offers. So if you have, let me know in the comments down below. I'd love to celebrate or celebrate on your behalf, because I'm super proud of you. Anyway, I will catch you in the next one.